Okay, in this section we will discuss mirror formula and linear magnification. And before this, we need to make ourselves familiarized with the notations which we will be using for representing object distance, image distance, object size, image size, linear magnification. So let's first understand those things. Suppose this is the concave mirror, this is the pole, it's a part of a hollow sphere, the center of which would be somewhere over here. Line joining P and C is the principal axis. Now do one thing, whenever you draw a ray diagram, just revise or try to recall all the definitions. And the central point, that is known as the principal focus. In the case of convex mirror, again try to recall, convex mirror is that spherical mirror whose reflecting surface is away from the center of the hollow sphere of which it forms a part. The center of the spherical mirror is known as pole. The line joining pole and the center of curvature is known as the principal axis. The midpoint of P and C is known as the focus. Right? We need to recall all these terms and definitions while drawing ray diagram. Okay. This we are aware. It is focal length. This is radius of curvature. This is focal length F and this is radius of curvature R. Right? Object is to be placed always in front of the mirror. Suppose this is the object. We will indicate it by AB. This is the object placed in front of the mirror. We will indicate it by AB. Suppose its image is formed somewhere over here. Let us consider its image to be formed somewhere over here. A dash, B dash. We will discuss the image formation. We will discuss it in detail. But here we will take a simple illustration. Suppose the object is placed over here and its image formed is like this. It is inverted. It is inverted. So this point A is represented by A dash. This is B. This is represented by B dash. Just to signify the fact that the nature of the image obtained is inverted. We'll discuss it. While in the case of convex mirror, it is always virtual erect and diminished in size. So its image will be obtained somewhat over here, behind the mirror, and it will remain erect over here. We'll discuss the nature of the ray diagram. Nature of the images formed in various cases. We'll discuss it in the later section, right? Anyway, this is the object. Object distance is to be represented by small letter u. This is the image distance. It is to be represented by small letter v. This is the object. So object distance will be represented by u. This is the image distance. It will be represented by v. So remember, all the distances are to be measured from the pole of the mirror, right? The distances of the object from the pole of the mirror, that is considered to be u. U is the distance of the object from the pole of the mirror. V is the distance of the image again from the pole of the mirror. So U, V, F, capital R, we are all clear about these terms, right? Now there is a term linear magnification. It is denoted by small letter L. Linear magnification. It is defined as ratio of size of the image to the size of the object. Now look, size of the image. This A dash B dash is the size of the image. Let us represent it by H2. This is H2. This is the size of the image. And size of the object, suppose we represent it by H1. H1 is the size of the object. So linear magnification is defined as ratio of H2 and H1. So H2 denotes the size of the image while H1 denotes the size of the object. Now here one thing I would like to make it very clear that linear magnification, let's discuss some cases. In case magnitude of M is greater than 1, it means that H2 by H1 is greater than 1, or it further implies that H2 is greater than H1. So in case where the magnitude of the linear magnitude is greater than 1, it means that size of the image obtained would be greater than the size of the object. It means that enlarged image will be obtained or magnified image will be obtained. So this is one of the cases. This is suppose case 1. Case 2. If mod of M is less than 1. So it means that h2 by h1 is less than 1 or h2 is less than h1. It is the case of diminished image, that is when the size of the image obtained is less than the size of the object. That is, in this case, linear magnification is less than 1. In this case also linear magnification is less than 1. Its size is less than that of the size of the object. And case 3, if m is 1, so it means that h2 by h1 is equal to 1 or h2 is equal to h1. Linear magnification of a spherical mirror is 1 only when the size of the image is equal to the size of the object. So we discussed all the 3 scenarios. Now sign convention is used in case of small m as well. If m is positive, it means that the image obtained is erect. It is for erect image. It is for erect image. If small m is negative, linear magnification is negative, it means that the image is inverted. So image is inverted. So this is regarding the linear magnification. So a question arises, what will be the linear magnification of a plane mirror? Now look, in the previous section we have discussed, in the case of a plane mirror, the size of the image obtained is exactly equal to the size of the object. Also, the image obtained in case of a plane mirror is erect. So m would be positive, and since the size of the image is equal to the size of the object, it will be equal to 1. So for plane mirror, the linear magnification is equal to 1. Linear magnification is equal to unity only and only in the case of a plane mirror. Right? So this is regarding the linear magnification. Now we will discuss mirror formula. Mirror formula is basically an expression relating object distance, image distance and the focal length of a mirror. And it is applicable for all types of mirror, whether you are considering concave mirror, convex mirror or plane mirror. This formula is applicable for every mirror. So it is a mathematical expression relating object distance, image distance and focal length of a mirror. The mirror formula is 1 by f is equal to 1 by v plus 1 by u. This is the mirror formula. We can also derive this relation, which we will do in the later section. This is just the intro part. U is the object distance from the pole of the mirror, V is the image distance from the pole of the mirror, F is the focal length again from the pole of the mirror. All the distances are to be measured from the pole of the mirror. And while solving numericals, you have to make use of the sign convention. That is, distances measured from the pole of the mirror along the direction of the incident ray is to be taken as positive, while distances measured against the direction of the incident ray is to be taken as negative. We have also discussed focal length of a converging concave mirror is always negative, while focal length of a diverging or convex mirror is always positive. So this is the mirror formula. It connects U, V and F. Linear magnification we have just discussed, it's equal to h2 by h1. Here also sign convention is to be used. For erect object, erect image, it is to be taken as positive. For inverted image, the size of the image is to be taken as negative, right? M is positive for erect image, M is negative for inverted image. So this is in terms of the size. In terms of the image and the object distance, it is given by minus V by U. This also will mathematically prove in the later section. So this is the formula basically. V is the image distance from the pole of the mirror, U is the object distance from the pole of the mirror. So these are the formulas or mathematical expressions relating F, U, V and linear magnification in terms of the object distance and the image distance. This is the image distance and this one is the object distance.